Hello everyone, Assalamualaikum warahmatullahi wabarakatuh and good day. So in this session, I will continue on the second section of the topic 4, Bode diagram method. Okay, so in this second section, basically we have few subsections. Start from introduction as well, which is the introductory or introduction of the Bode diagram method, that we can use the Bode diagram to represent the plot of magnitude or gain, and also the corresponding phase angle of the output or response of the system when we excite the system using the sinusoidal waveform. Okay. So basically, you can also refer to the textbook, which is the theoretical part about how we can represent the Bode plot on the logarithmic plot, Bode plot on the log paper. Okay, so basically, in terms of theory, you see that some of the notes been attached here, which is I've taken this from textbook. All right, so basically there are more longer notes you can see here, which is in this session, in this video session, I will talk more on my lecture notes based on the information in my lecture notes. Okay, basically the textbook is as a reference only. So in Bode diagram method, there are two things what we are going to display on the Bode plot, on the Bode plot. The first thing is we are going to observe the changes of the amplitude of the response, amplitude of the response signal, response or amplitude of the output signal, and also the phase angle of the output signal. So basically for the amplitude, we can represent it in the form of decibel. The decibel, the unit is dB, which is we will convert the power and represent the power gain in decibel. We are not going to represent it in the form of amplitude, but in the form of decibel. That is actually, decibel is, we convert this amplitude to power in the form of decibel using this expression. So basically, when we do the conversion to decibel, we use this equation 20 log 10 of ratio of the amplitude output to the input. Okay, so we take the ratio of the amplitude, do the log and times 20, which is power decibel. So basically for the Bode plot, we can also use tools like MATLAB to do the Bode diagram. We can represent the Bode diagram just by using MATLAB, put the codes and also plot it, and then we will see the Bode plot on in the form of MATLAB plot. But basically, what we're going to explore in this section or in this subtopic is we are going to know in more details how we do the manual sketching of the Bode diagram. Okay, so we can also estimate Bode diagram manually through analyzing built-in factors, using built-in factors in the transfer function. So basically, when we see the transfer function, it depends on the factor of the transfer function. For example, the first one is constant factor, meaning that if GS here is K, represented by a constant factor, what sort of Bode plot we can observe? So basically, if we use the constant factor, if the transfer function is represented by constant factor, It depends on whether the constant factor k is greater than 1 or k is smaller than 1, smaller than unity. You'll see that when we plot the magnitude of power decibel of k, okay, the magnitude, it should look like this if it should look like this, if it is k is over unity, over 1. If k is low, smaller than 1, for example 0.5, you can see the plot is below the uh, meaning that to the negative lah, to the negative of the vertical axis, which is the gain, the decibel, which is negative. For example, if k greater than 1, this is 20 decibel. But if k is smaller than 1, it is negative 20 decibel. So the output of a constant factor, output plot of the constant factor is constant transfer function like this. So meaning that k is constant, it is constant in terms of power decibel. The second factor is integral or derivative factors. For the integral factor, g of s is 1 over s lah, integral factor. For derivative factor, g of s is s. Okay, so we can represent integral factor as 1 over s, and derivative factor is as s. So if we plot the, if we use the Bode plot to represent the function or transfer function of gs, if that gs is belongs to the integral factor, then we will see that the magnitude plot will be like this. Okay, will be like this for the magnitude plot, and the phase angle plot will be like this, which is the phase angle plot. You see that it's a negative angle for the integral factor. Okay, and this is the negative slope of the magnitude. That is for the integral factor. On the other hand, for derivative factor, when you plot in terms of Bode plot representation for the derivative factor of transfer function of g of s, you will see that the opposite representation with respect to the integral plot. So you will see the curve should look like this, which is positive slope of the magnitude, and positive slope of the magnitude start from 0. And for the angle plot, it should be positive. It should be positive plot for angle. So this is the Bode plot for magnitude and phase angle for derivative factor s of the GFS. And the third factor is the first order factor. The first order factor, which is for the first order factor, the function should look like this, which is either it is 1 plus st or 1 over 1 plus st. So if that function, if that transfer function represented in the form of 1 plus st, what we can expect from the Bode plot that we will have is for the magnitude plot, it should start from 0, constant, and it will turn here, which is the corner frequency 1 over t. Okay, it will do some turning at the corner frequency here, and another straight line to the positive, to the increasing decibel. Okay, for the phase angle of 1 plus st, it should look like this, which is start from 0 degree and increasing angle toward infinity of when when omega increase, the angle will be increasing toward infinity like this. Similarly, for magnitude, when omega increase, start from 0 omega to infinity, at the corner frequency, there will be some turning, okay, toward the infinity like this. So that is for the function of g of s equals to 1 plus st. For another function of the first order function, if we have g of s is equals to 1 over 1 plus st, you will see the plot. We can expect the Bode plot should look like this, which is when we plot the magnitude, it will start from 0, constant. At the corner frequency, it will turn to negative decibel, to the negative decibel, straight line of negative decibel. Okay, toward the infinity as omega is increasing to the infinity. For the phase angle, also it should start from 0 and then decreasing toward the infinity as omega increase. So it is opposite after it reach it is actually the opposite relationship between 1 plus st and 1 over 1 plus st for the first order factors. So you should expect the Bode plot like this lah, for the corresponding 1 plus st or 1 over 1 plus st. All right. All right, moving on to 4.2.2 section, line approximation for magnitude plot. So how do we approximate line of the magnitude plot? You see the lines of magnitude plot like this. How do we approximate this line of the magnitude plot? All right, that is what we are going to do without any help of MATLAB or any help of the tools like software, for example. If we want to do the hand sketching or manually sketch the plot, so what we should do for the lines of the magnitude plot. This is what we have, how we can approximate. We should be familiar with log punya identities. Okay, so how do we approximate the line of the magnitude plot? Basically, the Bode plot use straight lines or asymptotes. So you will see the asymptotes here, straight lines like this. For the magnitude, you see the straight lines start from 0, horizontal straight lines, and another positive slope of the straight line. This is asymptotes lah. So when we represent that magnitude plot, basically we do the straight line like this, which is called as a asymptotes. So in this case, we can use some useful algorithm properties. You should understand when you do the calculus related to log, for example, you will see some of the rules related to log. When we do log, basically for log AB like this, it can be represented as log A plus log B. Okay, this is one example. So basically in estimating the transfer function of any system, we can use log. Okay, let's say if we have a system with G of S like this, with input and outputs, with input and output of a system G of S. So as here, as we want to do the Bode plot for the magnitude, the first case we will do for the magnitude. The first part we will do for the magnitude. So basically we will substitute S with J omega because we want to observe what is the behavior, what is the plot for the magnitude when omega is vary from 0 to infinity. Okay, so we substitute S with J omega. Let's say we have this particular system. G of S equals to G1 divided by G2 times G3 like this. So we can use the advantage of logarithm properties or log properties to further compute this system of G of S, it equals to G1 divided by G2, G3 here. For example, if we want to find the magnitude of the system here, power decibel for this system, the amplitude of this system. So basically, we can use the formula for power decibel 20 log G of S, amplitude of G of S, which is actually just now we have discussed about the ratio of the amplitude of output to the input, right? So basically, this is the amplitude representation of the function of G as a function of frequency, J omega. Okay, so we do it like this, 20 log G, which is G is actually this function, G1 divided by G2, G3. Okay, based on the logarithm property or log properties, the magnitude expression of G J omega can be written as this, right? So we can further extend based on the log properties. 20 log G J omega becomes 20 log G1 divided by G2, G3 in decibel. And we can pecah-pecahkan ataupun we can split it into addition lah, from this fraction G divided by G2, G3 here. We can split it into addition. Okay. So we can do the addition like this, which is equals to 20 log G1 plus 20 log 1 over G1. Bukan 20 log G2, bukan. But 20 log 1 over G2, which is bila kita guna plus. And plus 20 log 1 over G3. So basically when you use the log property of G1 divided by G2 times G3, okay, you can do it like this. So multiplication of the magnitude factors becomes addition. Multiplication of the magnitude factors become addition. So as you see in this lecture notes, therefore the individual magnitude plot for each factor will be algebraically added to yield the total plot of the Bode diagram magnitude. So also we can do for the phase angle. Once we finish doing for the magnitude, of course we would like to compute the phase angle as well for G J omega here. Basically for if G J omega has a combination of three functions, then we can do the addition of the phase angle as well. Phase angle as well using the log properties. For the angle of G J omega, it is angle of G1 plus angle of G2 and plus angle of G3. So that is the thing that we have highlighted before we go further discussing about constant factor, about the next section, which is when we want to sketch the Bode diagram. Basically, we should consider three different types of factor for the transfer function, whether it is the constant factor or integral derivative factor or the first order factor. Okay, so I will start with the constant factor first. So this is more detailed explanation about Bode diagram plot when in terms of individual factor. Okay, you'll see a lot of notes here that I will be discussing, and maybe I will focus on this note only in this remaining session. Okay, let me see constant factor, which is this one. Okay, this slide. I will start from constant factor A, referring to this particular slide. The information in slide is very little. but please keep focus on this lecture notes. Yeah? Okay, I will start with constant factor. So we express the magnitude of the constant factor k as 20 log 10 k because g of s is k. So because from the formula of 20 log 10 g, okay, let's say this is the magnitude. For example, if we want to find the magnitude, so g is equals to k as a constant factor, meaning that k is the magnitude's value in real number. Okay, for example, if k is smaller than 1, then we can estimate the plot of magnitude is positive magnitude. Let's say this is 20 decibel. It should be positive 20 decibel lah. For example, okay. Another case is when k is smaller than 1, we should expect the plot supposed to be the magnitude plot at negative. For example, this case should be negative 20 decibel. Okay, that is the thing when we consider, when we want to plot the constant factor, it is just easy, it's just straightforward. Depends on the magnitude value in real number. If k is smaller than 1, smaller than unity, then we can expect that, sorry, this is not k smaller than 1. Actually, I've done some mistake. This is k greater than 1. This is k greater than 1. You should expect positive decibel, positive 20 decibel, for example, in terms of value. If k is smaller than 1, then it is supposed to be negative magnitude, but constant. Let's say if we have a look at this example, for the first case, let's say if k is smaller than 1, this case is k is smaller than 1. For example, if k equals to 0.1, then when we do the calculation of the magnitude of g, when g is we expect the transfer function is smaller than 1. For example, this g or k equals to 0.1, then we do the calculation of 20 log 0.1, then we get negative 20 decibel. Okay, if k is greater than 1, for example, k equals to 10, when we do the calculation, we'll get 20 decibel. All right, so that is what we can do the plot lah. Firstly, we calculate for k of the calculate the magnitude, and then later what we do is to calculate the phi, which is the angle. Okay, so the phase angle phi is represented or can be calculated by using arctangent imaginary part of the transfer function divided by real part of the transfer function. In this case, we have g of s equals to k, meaning that we only have the real part, okay, plus 0 j. So imaginary part is 0, so meaning that arctangent 0 divided by k, so arctangent 0 is 0 degree. So meaning that we can expect the phase angle plot should be constant at 0 degree, constant at 0 degree. So when we plot for the different system, if k is greater than 1, we should expect that the positive 20 decibel, okay, constant plot of the gain. And if k is smaller than 1, or the other case, we should expect the plot is linear, constant, plot at negative 20 decibel for k equals to 0.1. So the gain here is constant for all frequencies start from 0 frequency to the infinity. it is moving toward infinity. Okay, so it is constant over the frequency spectrum, not over the time, over the frequency spectrum. For the plot of phase angle in degree, as we have calculated just now, if k is greater than 0, for k is greater than 0, then we should expect that 0 divided by k is 0, arc tangent 0 equals to 0 degree, meaning that for k is greater than 0, we should expect that the angle will remain constant at 0 degree for the range of omega start from 0 to infinity. Okay, but for phase angle, I didn't do the calculation, but basically for the phase angle, if k is negative, if k is negative, we should expect a constant phase angle at negative 180 degree, start from 0 to infinity. Okay, it should look like this for the constant factor. So let's have a look at a more realistic example of using this circuit. Circuit, if we inject this resistor with some current from this voltage. Okay, we have the voltage here. Inject some current to this resistor. Okay, basically we can represent it in the form of time function V equals to IR. Okay, rearrange this equation Vt equals to ITR. Then we substitute T with S to represent this equation in the form of J omega of frequency. Then we can do the transfer function of S of this is the transfer function of the system. Let's say this is G of S, for example. So G of S is equals to IS divided by VS and equals to 1 over R. So this example gives us that GS is actually K. GS is actually constant function, constant factor. All right. So this is an example of the G of S of represented by a constant factor when we represent the, because this is R, that's why it is constant factor. It is constant factor. If this branch is capacitor or the inductor, suppose that it is no longer linear like resistor. Okay. All right. Moving on is the integral derivative factor. Okay, integral derivative factor. So in this integral derivative factor, it is useful for us to consider the log properties, which is about the number with its reciprocal relationship. For example, if we have k, then its reciprocal is 1 over k. Then if we represent it in the form of power decibel 20 log k, suppose that we can rearrange this log function to negative 20 log 1 over k. So this is k and that is the reciprocal. Okay, so let's say for this case, integral derivative factor here. Let's say if k equals to 10, so we can represent the power decibel in terms of 20 log 10. Then, of course, if it is 20 log 10, then suppose that log 10 of 10, it becomes 1, right? So it is 20. But if for reciprocal of k, which is 1 over 10, if we substitute in power decibel here, 20 log 1 over 10, suppose that we can get the negative 20. So if we can rearrange this, negative we put here to the left hand side. This negative we put to the left hand side. Meaning that we can represent it like this lah. 20 log 10 is equals to negative 20 log 1 over 10. Okay. Suppose that is the same lah. 20 log 10 is equals to negative 20 log 1 over 10. Alright. Okay. That is what it means by when we bila kita jumpa dengan reciprocal relationship of the system, when we do the integral derivative lah. When we do the integral derivative, we will see this relationship. So it is easier for us to represent. For example, if we see that we have the function of 20 log 10, then we can represent it in the form of negative 20 log 1 over 10. So let's see one example. Example of the integral factor like this function. So if we have g, we want to calculate the integral factor of g, 20 log 1 over j omega for this function. Example, okay. 20 log 1 over j omega. Let me check. Actually, I've made another mistake here. This is not g of s equals to 0 plus j omega. So it is g of s equals to 0 plus 1 over j omega lah. Because g of s represented by 1 over j omega. So 1 over j omega here. This is g of s. So when we do the power decibel for g here, we do it like this as usual, 20 log 1 over j omega. But since this is since this form has the relationship of reciprocal of j omega, so this is reciprocal of j omega, which is 1 over j omega, right? So we can convert this equation or function to negative 20 log j omega, so that in this form, it is easier for us to do further calculation. All right. So we convert it to negative 20 log j omega. So it is easier for us when we do this magnitude calculation. Okay. Basically, it is omega. Okay. Basically, it is omega. All right. So it becomes negative 20 log omega for the magnitude. And then similarly for the calculation of phi or phase angle, we can use the reciprocal relationship of the system, which is now negative arctangent omega divided by 0. Negative arctangent omega divided by 0, which is this is from g of s equals to 0 plus 1 over j omega tadi. Okay, so in this form, when we have this sort of reciprocal of the j omega here. Okay, so we can do it in the form of tangent omega divided by 0, which is infinity. All right, so negative arctangent infinity is negative 90 degree. Okay. Negative arctangent infinity is negative 90 degree, which is negative angle. Okay, so we have one single frequency here, which is omega. Okay, so when we do the integral factor of this particular function of g of s, so we can basically use the reciprocal relationship of the constant. Then we have a negative 20 log omega for the magnitude, and for the phi or angle, we have negative 90-degree angle at frequency omega. Let's say if I want to plot the integral factor function here. Okay, let's obtain a G for several frequencies separated by decade. 10, 10, 10, 10, kan? Alright, let's do for magnitude of G at several frequencies. Start from, let's say I have omega equals to 0.1, the first point of omega. Okay, so substitute in the equation, G equals to negative 20 log 0.1, then we get 20 decibel. And then next is at frequency of omega equals to 1, we do the calculation of G, negative 20 log 1, which is 0 decibel. And moving further from 0.1, 1, and 10, omega equals to 10. So omega starts from 0.1 and 1 and 10 and 100 and 1000 and so forth in the log scale. All right. So moving on to omega equals to 10, substitute in the equation negative 20 log 10, then we get negative 20 decibel. So you will see that the change of power decibel, the change of magnitude from 20 to 0 to negative 20, constantly changing at at a constant negative slope, right? At constant negative slope like this. So when we do the plot, we can expect that our plot of Bode plot should look like this for the magnitude. Start from let's say this is omega. Kita tak nampak sangat, but it is actually 0.1. At the point of 0.1, frequency equals to 0.1, it should start from 20 decibel. And at the point of 10, frequency equals to 10, it is negative 20 decibel. So and so forth. At the point of 1, frequency equals to 1, it is 0. At the point of nearly 100 here, frequency, it is supposed to be negative 40. So when we do the plot, it is the slope of negative slope. Negative slope. This is the plot of the magnitude for integral factor. Integral factor meaning that integral factor is 1 over s, right? Integral factor. So derivative factor is s. Okay. So we will get this negative slope. When we do the Bode diagram for the magnitude of the integral factor, we will get the negative slope like this. And then when we do the calculation of the angle, see that the angle is negative tangent, negative arctangent omega divided by 0, which is negative arctangent infinity, which is negative 90 degree. Negative angle 90 degree, we can expect that the phase angle plot supposed to be at constant negative 90 degree angle. All right. So we can do the plot like this for the phase angle. Even though if we substitute with omega equals to 0.1, omega equals to 1, omega equals to 10, omega equals to 100,000, and so forth, for the phase angle plot, we will see that the result is always at negative 90 degree constant. Okay, for the phase angle plot, because even though if we change omega here for this particular equation, even though we change omega, it is always arctangent infinity. Always arctangent infinity. So we should expect the constant plot, even though we change the frequency. Alright. Okay. So the plot for the phase angle plot should look like this at negative 90 degree, even though we change the omega. So that is for integral. That is for the integral. Now moving on to the derivative factor. So derivative factor is which is G equals to J omega. Or in other words, it is basically G equals to 0 plus J omega. Just now, we are talking about G equals to 0 plus 1 over J omega, which is the integral factor. But this time, for derivative factor for this function of G equals to J omega, when we do the power decibel expression, 20 log magnitude of J omega, so it is 20 log omega. It is 20 log omega, right? So if you don't know this, how do we get 20 log? If you don't know why do we get omega here, you should refer back to the theory in the textbook. Basically, if I'm going to explain to you, it should be like this. It is G actually equals to J omega magnitude equals to 0 square plus omega square root, then it is square root of omega square, then it is omega. That is why we get omega there. All right. Okay. So that is for the magnitude plot of derivative factor 20 log omega. Then for the equation of the phase angle, we don't do the reciprocal now because it is straight. It is derivative factor. It is just straight. So it is phi equals to arc tangent omega. But still, omega imaginary part divided by real part. Real part is 0 in this case. See, real part is 0. This is imaginary part. Imaginary part is omega. Real part is 0. Still, we get omega divided by 0. But positive arc tangent. So arc tangent infinity is 90 degree. It's 90 degree, right? That is for the phase angle. So it is different to the integral factor. It is negative angle, but on the other hand, for the derivative factor, it is positive angle 90 degree. So we can do similarly for the integral factor. Calculate the several frequencies for the derivative factor. Start from omega equals to 0.1. Okay, substitute 0.1 here, then we get negative 20 decibel. So for the magnitude of omega equals to 1, we can get 0 decibel. And further, as the frequency increase to 10, okay, frequency increase to 10, then we do the magnitude G equals to 20 log 10, then we get 20 decibel. So when you see this, you should start from negative 20. Suppose that this is somewhere around here is negative 20 decibel. Okay. So the first point at 0.1 frequency. Okay. Omega equals to 0.1. And then omega equals to 1, it is 0. And omega equals to 100, somewhere around there, it is 40. It is 40. So when we do the plot, suppose that the plot should look like this, which is positive slope. Positive slope. So we can observe that the magnitude change when the frequency change from 0 to infinity. The plot should look like this, which is positive linear plot like this. Okay. And for the angle, of course, when we do the angle arc tangent of the derivative factor, arctangent infinity, we get positive 90 degrees, so that it is always constant over the frequency range start from 0 to infinity, so that we can plot it like that. All right, that is for the angle. So this is the representation of the Bode diagram for the derivative factor. If you compare with the Bode diagram of the integral factor, it is basically opposite lah. It is basically opposite for the corresponding magnitude and phase angle plots. So we can conclude here for the integral and derivative factor. Notice that from both 1 over s, which is the integral, and s for the derivative plot, magnitude plot opposite one another in terms of slope. Okay. Okay. For derivative, for the integral, it is negative slope. For integral, for the derivative, it is positive slope. And then for phase angle, they are different in their sign. So negative angle for integral, okay, and positive angle for derivative. All right, that is what we can conclude when we plot the Bode diagram for the integral factor and also derivative factor of ds. The third one is first order factors. First order factors. The function of the transfer function for the first order factors, either it is a function of g equals to 1 over 1 plus s, either it is a function of g equals to 1 over 1 plus st like this, or g equals to 1 plus st. I will start from the function of g equals to 1 over 1 plus st, in which, as usual, we want to observe the plot when we change the frequency start from 0 to infinity. So we want to observe the across the frequency spectrum, what is the behavior of the magnitude and phase angle of this first order transfer function of g equals to 1 over 1 plus st. We do the similar way like we have done before, which is calculating the power decibel of the magnitude. G equals to 20 log this function, substitute s equals to j omega. Okay, so we should calculate log of this magnitude, and we have learned about the reciprocal relationship of the function, right? So if we put this as a numerator 1 plus j omega t, then we should put negative. We should put negative to this function. So negative 20 log 1 plus j omega t, so that it is easier for us to solve this magnitude. So negative 20 log this magnitude, then we can divide this into several areas of low frequency range. So if we have this axis of omega, suppose that we can divide it low frequency range of omega, which is omega t is smaller than 1, and high frequency range defined as omega t is greater than 1, like that. So we'll start calculate for omega t is smaller than 1 for the low frequency range. So how does the magnitude plot should be in low frequency range? So we do the calculation. G equals to negative 20 log omega t is smaller than 1, for example, omega t equals to 0, then should be this is 0, should be this is 0. So the magnitude is 0 when omega t is smaller than 1. For high frequency range, omega t is greater than 1. Let's say omega t is a very large number. Then what we see in this square root, suppose that it should be like something that we take the power of 0. Should like this term becomes 0 and this term is large enough so that we cannot neglect this term, which is we keep it as omega t squared. So we solve this, then we get negative 20 log omega t for the high frequency range. Okay, for the low frequency range, okay, low frequency range, bahagian low frequency kita akan dapat magnitude sebagai 0. But for the high frequency range, when omega t is greater than 1, we should expect that we will get the magnitude of negative 20 log omega t. Okay, so we have a pair of magnitude, whether it is at low frequency range or high frequency range. Whether it is at the low frequency range or high frequency range. To sketch the plot, we should obtain the magnitude at different frequencies. Okay, let's say if the frequency is 1 over t. Okay, if the frequency is 1 over t, because this is omega t, it is we represent omega equals to 1 over t so that we can cancel t lah. So that this one becomes 0. So for the case of omega equals 1 over t, then we get negative 20 because this term becomes 0. So it is 0 decibel. 0 decibel for the gain at omega equals to 1 over t. And then further increase the frequency at omega equals to 10 over t. Then we do the calculation. T is cancelled here. So log 10, meaning that this term becomes 1. Then the gain for omega equals to 10 over t is negative 20. All right. And then as the omega increase to 100 over t, then substitute in this equation, the gain is, this term becomes 2 when we cancel t. This is 10 power of 2. Then this is 2. So negative 20 times 2 is negative 40 decibel. So we see the increase of the gain from 0 to negative 20 to negative 40 decibel. That is for the magnitude. For the magnitude. But when we want to do the plot, of course, we'll need to consider the phase angle as well. Okay, the phase angle by definition. For the phase angle, by definition, the corner frequency. What is corner frequency? We should expect for the case of first order factors here, the function is no longer constant over the frequency range. It should be something like dia straight, then dia patah. Dia straight, then dia patah macam tu. So we should expect that low frequency range area and high frequency range area. But in between the low frequency range and high frequency range, there is the corner frequency. The corner frequency. So to determine the corner frequency, basically we can determine the corner frequency, which is a frequency which is low frequency magnitude equals to high frequency magnitude. Okay, low frequency magnitude equals to high frequency magnitude. Low frequency magnitude is 0 decibel as we have calculated here. Low frequency magnitude is 0 decibel equals to high frequency magnitude. That is the equation. Equals to high frequency magnitude is which is negative 20 log omega t. So 0 equals to negative 20 log omega t. Further calculate this, we get the frequency, which is the corner frequency here, is omega equals to 1 over t of the corner frequency. Using this what we call as definition, using this definition. Okay, so when we find the corner frequency means we have the asymptotes of straight lines like that, and it should, at corner frequency, it should turn either is to negative downward or upward. Okay, right. Okay, so when we get the corner frequency, then we can do the angle of another frequencies. So we should start with corner frequencies, the middle one first. Then we find the frequency at lower frequency range, and also the angles at higher frequency range. Okay, so we start calculate phi for the lower frequency one. Phi equals to arc tangent 1 over omega t. Okay, arc tangent 1 over omega t, because this is the first order transfer function of g equals to 1 over 1 plus st. Suppose that it is 1 over j omega t, right? For this one. So we calculate arc tangent 1 over omega t. So this is the reciprocal for omega t. Then we can do this as negative arc tangent omega t. Once we get this equation, we can substitute from zero frequency range, which lower frequency range, which is omega equals to 0, for example. Substitute arc tangent, negative arc tangent 0 is 0. And then at corner frequency, at omega equals to 1 over t, substitute phi, negative arc tangent at corner frequency 1 over t. Suppose that phi equals to negative 45. Then when omega approaching infinity, we can substitute omega equals to infinity for this angle. Phi equals negative arc tangent infinity, which is negative 90 degree. So we get 0, start from low frequency range, and then negative 45 at the corner frequency, and at the frequency approaching infinity, we will get the negative 90 degree. Then when we get all of those magnitudes and phase angle, then we can do the plot, the Bode plot. So we will do it like this. Okay, at 0.1, 1 over t, 10 over t, and 100 over t of frequency. Then we plot plot one by one. But make sure that you should keep the lines of the corner frequency here. Should keep the make sure the lines of the corner frequency at 1 over t because corner frequency is 1 over t. So this range is the low frequency range of the magnitude. This magnitude plot is high frequency range of the magnitude. So in low frequency range, the magnitude is 0. Okay. At high frequency range of omega, the magnitude, when omega approaching infinity, the magnitude is negatively increasing. Can we say that? All right. The magnitude is toward the negative gain. Negative gain. So for the high frequency range of the phase angle, we should expect it is changing from 0 degree to negative 45 degree at corner frequency. So at corner frequency, then at high frequency range, it start from negative 45 degree to further until negative 90 degree when it approach infinity. Suppose that if we further increase this, it should maintain at negative 90 degree lah. Dia tak sentuh pun, tapi dia akan maintain lah. Dia punya lines ni akan maintain sampailah infinity lah. Alright, so saya nak padam sikit ni. Okay, yang terconteng padam. Bagi cantik sikit. Alright, so that is how we do for the 1/1 plus st function of the first order transfer function lah. For the first order transfer function, where the function is g equals to 1 plus st like this. Basically, I just summarize it. Basically, what we should expect when we do the plot of the first order transfer function of 1 plus st here. For this function, we shall have the similar but opposite magnitude plot and opposite sign of phase angle. Alright, so let's say this is the function of 1/1 plus st. Dia akan constant at 0 for the magnitude sampai dekat corner frequency, dia akan patah ke bawah. Alright, dia akan corner terus straight line ke bawah sampailah infinity. Yang ni untuk g equals to 1/1 plus st. But for g equals to 1 plus st, dia akan start mula daripada 0 juga constant sampai corner frequency, dia akan patah ke atas. Dia akan patah ke atas macam tu. Sampailah infinity. Okay, itu maksudnya opposite direction dekat corner frequency. Begitu juga yang ni phase angle tu dia akan mula pada kosong dan ke positive angle. Mula pada kosong ke positive angle sampailah bila dia sampai ke 90 degree tu, dia akan keep approaching the 90 degree sehingga infinity lah, right? Ni saya tunjuk macam ni saja, just like that. But basically you should understand that for this angle of the 1 plus st first order transfer function, the angle should start from 0 and to the positive angle until 90 degree. So it will meet at 45 degree at the corner frequency. Corner frequency 1/t 45 degree. So that is the thing that we should expect. So that is actually the discussions about the Bode diagram method. In our next session, I will show you in the form of example how we can plot the Bode diagram method using the example example-based explanation, so that it is much more easier for you to understand. I will stop this video up to this time because I'm going to continue that video. Okay, thank you. Assalamualaikum.